This is the common system studied in what we call classical physics. This system essentially describes how springs work. When you stretch out a spring, it wants to pull you back, and when you compress a string, it wants to pull you forward. We write the force as minus kx. What this essentially means that there is a force that is opposite and proportional to the position. If we decide to visualize the system in terms of potential energy, we get a surface shaped like a parabola. This tells us that the energy increases with the square of the displacement. You could imagine this as a mass oscillating in a valley between two parabolic-shaped hills. We can get a bit more mathematical too. Newton said that the force is equal to the mass times acceleration, and for those familiar with calculus, acceleration is the second derivative of the position. We can denote this with x double dot. Therefore, we can write this equation, mx double dot equals minus kx. We can rewrite this using the angular frequency, where we define the angular frequency as the square root of k over m. So now this equation becomes x double dot equals minus omega squared x when we cancel out the m. This is what we call a second order differential equation, and this has a general solution of x of t equals a cosine omega t plus b sine omega t. But what are a and b? Well, these depend on the initial conditions, that is, where the mass starts and how fast it was moving. If we let x of 0 equals x naught and x dot of 0 equal v naught, then we get that a equals x naught and b equals v naught over omega. So our solution to this equation becomes x of t equals x naught cosine omega t plus v naught over omega times sine omega t. In theory, this system will oscillate forever, but in reality, we know there's usually some friction or dampening, so we can add that next. To add dampening, we introduce another part of the force, a force proportional to the velocity, that is F equals minus b x dot. We can add this term to our Newton equation. It turns into this form, and we can define a new omega naught, which is equal to b over 2m. This omega naught is sort of a natural frequency to the system. Now the differential equation becomes this. The solution to this equation is a bit more tricky than the last one, but we might think of a guess to be the form of x of t equals a exponential alpha t, as derivatives are multiples with alpha. Here is the function, the first derivative, and the second derivative all shown. We can plug these into the differential equation. We can factor out the a exponential alpha t and divide it out, and we get this equation. Now this equation is a quadratic equation for alpha, so we can solve it using the quadratic formula and arrive to this. So our solution relates to alpha, yet alpha relates to omega naught and omega. So depending on how omega naught relates to omega, we will have different cases. So the first case we're going to talk about is when omega naught is greater than omega. In this case, we call it overdamped. Here is the solution to the equation. In this case, the square root is real. And this is how the spring works. Remember that omega naught related to our b term, and that b term related to the friction or the damped force. So in this case, the damped force is much greater than the restoring force. This causes the mass to slowly return to its normal position. The second case we have is when omega naught equals omega. We call this case critically damped. Here's the solution you might expect, but there's also another solution due to the effects of differential equations, so the overall solution is actually the addition of these two. Here's the solution with initial conditions, and here's how the spring works. The spring goes much faster towards normal position as compared to the overdamped case. The next case we have is when omega naught is less than omega. We call this case underdamped, and the square root term is actually negative, so we can actually factor out the square root of negative 1, also known as I. Here's the solution to this part. Here is the terms for A and phi depending on the initial conditions. And finally, here's how the spring works. It actually oscillates back and forth with a decreasing amplitude. Thank you for watching this video. It's one of my first ever. I hope you guys liked it. Please like and subscribe, and thank you.